Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Today's topic of discussion is Ohm's Law and electrical safety. Our objective is to apply Ohm's Law to scenarios involving electrical safety. Additionally, we'll discuss safe work practices when performing electrical work. This lecture does not cover circuit protection devices like fuses, breakers, and ground fault current interrupters, nor does it cover grounding and bonding. These topics, also related to electrical safety, will be addressed in later lectures. This topic is an extension of the General Industrial Safety lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, only dimly recall its contents, by all means take the time to do so now. The same caveats I gave during the General Industrial Safety lecture apply to this one as well. The topic of electrical safety is far too important and far too large to be covered in a single online lecture. If you are seeking formal safety certification, I recommend you visit your local community college or a reputable and recognized service provider. This lecture's only purpose is to provide general electrical safety guidance and gives us a chance to apply Ohm's Law to these scenarios. My intention is that you understand, appreciate, and respect electricity, not fear it. It is as dangerous as it is useful, and there are laws, natural and man-made, that govern its wise use. If you've been following this playlist in its intended sequence, you may be shocked, pardon the pun, to find a lecture on electrical safety appear so late in our discussion. Customarily, safety is the first chapter of most textbooks, and presented in such a sequence implies high priority. This is the wrong way to do it, because electrical safety is absolute nonsense without an understanding of Ohm's Law. It is my intention that this series provide you with a progressively expanding skill set that will allow you to apply previously obtained knowledge to an ever-growing pool of applications. Today, we'll use our newfound understanding of Ohm's Law to understand electrical safety. For those with an understanding of Ohm's Law, a saltwater-soaked person standing on a metal platform touching a bare high-voltage wire is an obvious recipe for disaster. This is all kinds of dumb, and your newfound appreciation for Ohm's Law tells you so for several compelling reasons. First, everything is a conductor. However, some conductors are better than others. A saltwater-soaked person is an especially good conductor with low resistance. Second, a metal platform is also a low-resistance conductive path connected to Earth, something we often use as a reference for voltage measurements. Third, the wire is high voltage. The magnitude of this voltage is often made with reference to ground, that same plane the worker is connected to via the metal platform. If the worker touches the wire, there is a high voltage differential across a low-resistance path and substantial current will flow. The magnitude of this current via Ohm's Law is directly proportional to voltage and inversely proportional to resistance. If the voltage is high and the resistance is low, the current will be extremely high. Let's take this simple analysis one step further and look at it from the perspective of power and energy. With both high voltage and high current, the power transferred to this worker is high, because power equals voltage times current. If energy is power times time, if the conductive path is sustained for a long time, the energy delivered to the electrocuted worker will be high. Customarily, I've been speaking about energy as if it was a force applied for a distance, because the joule, the SI unit of energy, can be represented as a newton of force expressed for a distance of 1 meter. However, different forms of energy exist, in this case, notably thermal. Depending upon your choice of units, joules of energy could be equated to either a BTU or a large calorie, where a BTU is the heat energy necessary to raise the temperature of a pound of water 1 degree Fahrenheit, and a large calorie is the heat energy necessary to raise the temperature of 1 kilogram of water 1 degree Celsius. 1 BTU is equal to about 1,055 joules, and 1 large calorie is equal to about 4,186.8 joules. Water heat's nonlinear, and there are a bunch of different other considerations, but let's just say these are pretty close figures. The point being that electrical energy can be changed into heat energy, and this, among other deleterious effects, is what makes high current flowing through your body a situation to be generally avoided. Given an understanding of Ohm's Law and power and energy calculations, think about the simple steps you need to take to avoid inadvertent transfer of energy, i.e. a shock, when working on an electrical system. Step 1. Avoid high voltage. If voltage is high, current will be high. Here's an even better idea. Avoid voltage altogether. Turn it off, lock it out, tag it out, and test it. Verify that all sources of hazardous energy are removed. If you don't have to work on energized equipment, don't do it and turn it off. Lock it out and tag it out. Step 2, don't be a low resistance path. An insulator needs to be between you and high voltage sources. Make sure your listed personal protective equipment is dry and passes daily inspection. A common piece of personal protective equipment associated with electrical work are rubber gloves. Rubber has a high resistance. Rubber is an insulator. Current through high resistance paths should be low. Step 3, if all else fails, don't get shocked for long. If energy is power times time, the longer you are a conductive path, the more energy will be transferred to you. It is for this reason systems often incorporate protective mechanisms such as fuses and ground fault current interrupters to limit the length of high current or fault current events. We'll examine these devices in later lectures. Step 4, follow the law. This is probably the one and only time in this lecture series I'm not referring to Ohm's Law. I'm saying follow the appropriate laws governing safe work practices. There is absolutely no reason for you to ever be exposed to high voltage while you are a path of low resistance for an extended period of time. They are mandatory laws and safe work practices established by governing bodies, specifically OSHA and the NEC, or National Electrical Code, established by the NFPA. Obey the law. It's there to protect you. Finally, step 0, meaning before all these other considerations even come into play, know what you're doing. Don't just flip switches and push buttons. You are going to get yourself or someone else killed. A lot of industrial accidents aren't caused by reckless or careless people. Some accidents are caused by well-meaning people simply lacking the knowledge to do the job they've been pressured into doing. Don't do things you don't understand. I am more than willing to admit there are things that I can't do or don't understand, like listen or care about people's feelings or any of that other made-up stuff. I just don't do those things well, and I am not going to pretend I do. If you're being pressured into doing something you don't understand, don't do it until you're absolutely clear that no one's going to get hurt. People's lives might be on the line, and one of those lives might be yours. Here are some general safe work practices you should follow in working with electricity. Never work alone. If your team is working remotely, stay in contact with your operations and maintenance organization using radios. Turn the power off. Certain measurements must be made with the power on, but if all possible, turn it off when connecting instrumentation, then turn it back on to make the measurement. Never modify a circuit with the power running. You could accidentally short circuit critical current controlling elements. This is especially important when incorporating ammeters into a system. High power circuits need to make and break connection using devices rated to make and break that high current. Discharge or lock out any electrical energy storage elements like batteries or capacitors. Even if this system is unplugged, such energy storage devices can energize this system. Know where the emergency off button is. Have an exit plan. Have 3 exit plans and know where the fire extinguisher is. A fire extinguisher isn't there to put out fires, but rather clear a path to one of your exits. Use personal protective equipment, including safety glasses. Remove conductive jewelry like rings, and if you got long hair, tie it up out of the way. Never, ever wear a tie or a scarf around rotating mechanical equipment. Matter of fact, never wear a tie ever. Insulate your body. Use tools with insulated handles, and don't become part of a conductive path. If at all possible, work one-handed and maintain clearance by not leaning on other parts of the equipment. This ensures a conductive bridge isn't formed through your body. Before we move on to the rest of this lecture, let's get this out of the way. There's this saying that it's not the voltage that kills. I just can't even finish it. It's so stupid. You know what I'm saying. If you don't know what I'm saying, just let it be. Trust me, you're better off. The statement is stupid because without voltage, charges won't move. This is like saying it's not the gun that kills you, it's the bullet. Listen, you can take a 62 grain M855A1 5.56 millimeter enhanced performance round with a solid copper core and a steel penetrator tip and chuck it at a brick wall as hard as you possibly can. But after a couple tries, you realize maybe using an M4 carbine might yield better results. The rifle makes the bullet move. Voltage makes current move. The bullet won't move without the rifle firing it. Similarly, current won't move without voltage. High voltage will kill you because high voltage causes high current and low resistance paths.